Hello folks, StylePoint here, and today we're going to be implementing the tanh activation function. We're going to be implementing it in Python using PyTorch. But before doing that, let us first discuss tanh and compare it to some other activation functions. Okay, so here's the tanh activation function. Here's its plot, and here's the formula. So tanh of x is e to the power of x minus e to the power of minus x over e to the power of x plus e to the power of minus x. Now we also have these like alternative representations, or like the alternative formulas to the right, two of them. But this is the first one here, the first representation, first formula is pretty much the only one we need to know. These two could be derived by manipulating this formula. Okay, so if we multiply both the numerator and the denominator by e to the power of x, we're going to get this representation. And if we're going to multiply both the numerator and the denominator by the e to the power of minus x, we're going to get this representation. And the reason we have these like two additional representations or formulas is because we're going to be using them in the actual implementation. And that has to do with the numerical stability. But before getting into that, let us kind of concentrate or talk about the plot here. So this is the tanh activation function, right? This is the plot. And this is how it looks. It's like any fixed real number is going to be mapped onto a -1, 1 interval. Okay. Now the shape of the activation function of tanh, basically, it probably reminds us of some other functions. And one of them is activation function. It's sigmoid. If you don't know about sigmoid, I would encourage you to go and watch the video we have about sigmoid. This is how it looks. Again, very similar to tanh. And then there is this other function. It's usually not used as the activation function on its own. It's called cumulative distribution function, or the CDF. But this, I think, looks even more similar to tanh than sigmoid, right? This is CDF, this is tanh, right? The reason for that is because both of them have like flat upper and lower tails. Right. In case of sigmoid, these tails are more like smooth, right? They are smoother. They have these smoother transitions here. Now, CDF, as already mentioned, this is not used as the activation function on its own. Usually, it's not used. I mean, one could use it, but it's used for implementing GLU. So GLU of x, or the Gaussian error linear units of x. This is an activation function. That's going to be x times CDF of x. So if we scale this by x, we're going to get that activation function. So I would probably also encourage you to go ahead and watch that video as well. But again, not necessary. But tanh, sigmoid, and CDF, a lot of the things that these two functions provide, or a lot of the benefits that sigmoid provides, tanh also provides. Okay, so for instance, both sigmoid and tanh, they introduce nonlinearity, and that's super cool because otherwise we would not be able to approximate nonlinear functions. Now, CDF also, of course, introduced nonlinearity, but again, it's not used as an activation function. Usually, it's not. Now, sigmoid. One of the features of sigmoid is that it maps any fixed real number onto 0-1 interval. So that's like one of the powers of sigmoid. As a result, sigmoid is used as like a last pretty much layer in the deep learning or ML models, because any fixed real number is going to be mapped onto a 0-1 interval, and that can be interpreted as a probability. Now, we cannot say the same about tanh, because the tanh, it's going to map any number onto a -1, 1 interval, and we cannot really interpret that as the probability. Now, both sigmoid and tanh, of course, they have these three segments, a lower tail, upper tail, and like the middle segment, right? And of course, the cumulative distribution function has like the same feature. This can be seen as like a drawback in a way, because it hinders the ability of a neuron to express itself. What I mean by that is that not only do these activation functions, in this case I mean tanh and sigmoid, not only do they map the input onto this 0-1 interval, well, in case of tanh it's -1 to 1, so in both cases we map these inputs onto these fixed intervals, right? So that limits the expressiveness of a neuron. That means any number is pretty much condensed or like mapped into this small interval, right? So we don't have like a diversity, a big like diversity of values, right? But in addition to that, looking at the plot of tanh as well as of sigmoid, both of them, they have like these three clusters where most of the points are like concentrated. This is like the upper, middle, and lower like clusters, like these two tails in the middle segment, same as sigmoid, right? And that means that tanh it kind of, especially for very small negative numbers or negative numbers that have a very large absolute value. For those numbers, we're going to get closer and closer to -1. At some point, we're going to run out of the precision and we're going to get -1s. And for very large positive numbers, we're going to get 1s all the way. So we have that problem of mapping a lot of the values to the same number, right? Or numbers that are close to each other, like in these segments. So that can be viewed as like a drawback in a way, like kind of like a problem in a way. But sometimes this feature can be useful in case of sigmoid. That would be for like binary classification. There's like an extension of sigmoid that can be used. It's called softmax for multi-class classification. So sigmoid has this kind of an advantage of being useful for classification because any number in the 0-1 interval can be interpreted as a probability. In case of tanh, tanh does not even have that kind of feature, and it does not provide. Its output cannot really be interpreted as a probability. So tanh, you cannot really use it in the like the output layer or the last layer, but it's usually used in the intermediate layers. But I think in general, it's better if we don't use tanh and we use something like ReLU, because ReLU is going to be faster. Okay, I would encourage you to watch the ReLU video as well. But tanh also actually suffers from what's known as the vanishing gradient problem. I have not discussed this in any of the activation function videos because I think the vanishing gradient problem, it deserves its own video. So we're going to have a separate video about it. But what vanishing gradient means is that the gradient of tanh, and sigmoid actually has the same problem. Both the gradients or the derivative of sigmoid and tanh, they have this property that it's kind of, they obtain the value of 0. It's easy to get their gradients equal to 0. So a lot of times they can be zeroed out. And that means that in the chain rule, when we do a backpropagation, so if we get even 1, 0 in the chain rule, the whole gradient is going to be 0. And when we update weights and biases, we're not going to get any updates because we're just pretty much adding or subtracting like zeros. And that basically is a big problem because there's no learning happening. But again, we're going to have a separate video about it. So now that we know what is tanh, I'm going to briefly talk about this representation here. So if we use this representation, if x is a very large positive number, like 10,000, then this is going to overflow, okay? And if we actually do this in PyTorch, okay, if we, let's suppose, import torch, and if we do, let's define this, and I have already done this actually. I've tested this in PyTorch. So PyTorch has this very nice, I would say it's nice. I'm not sure if it's very nice actually. Feature that for very large numbers like x, it's going to say it's infinity. It's so large in like Python. If we did that, math that x of 10,000, it would overflow. It'd say overflow error, math range error. So Python says, I don't know, it's larger, so large, the number is so large I cannot really represent it. But PyTorch says I cannot represent it, but I'm going to give you this like abstraction or this syntactic sugar and call it like tensor inf. Like the number is so large that we might as well call it infinity. We cannot represent it. And one of the features about one of the kind of operations that it supports is like, for instance, division, right? So you can divide like 1 over infinity and it's going to say that's 0, okay? Infinity over 1, that's going to be infinity. Now, if we implement tanh using this formula, right? So e to the power of x minus e to the power of minus x, well, for very large x, this is going to be infinity, and the numerator is going to be infinity, and the denominator is also going to be infinity, and we can see that here. So this is infinity, and that is infinity too. And so if we divide infinity by infinity, PyTorch is confused pretty much. It says, okay, that's like nan, like not a number. It's like, okay, PyTorch says like, I don't know what you're talking about. Like, I don't know what is infinity over infinity. I don't know how to compute that. So I don't know what that equals, right? I mean, tensor infinity, that's of course is not necessary. I mean, it's not strictly correct, right? We can never get a value of infinity. We can only approach infinity. That's why in the limits we get as x approaches infinity, as something approaches infinity, but we can never be equal to infinity. So, but infinity over infinity, okay, PyTorch says, I don't know what that is. So eliminate these kind of problems. We can say for negative x's, we're going to use this representation. And for positive x's, we're going to use this representation. And so if x is a very large positive number, like 10,000, then minus 2x is going to be minus 20,000. And e to the power of minus 20,000, that's going to be 0. So we're going to run out of the precision. But 1 minus 0 over 1 plus 0, that's 1 over 1. And we know that's 1, right? So even in PyTorch, torch dot, well, x here. And if we do minus 2 times x, that's 0. So we know that 1 plus 0, that's 1, right? So we're going to use this, basically. So this kind of a trick. So for negative x's, we're going to use this representation here, right? And for positive x's, we're going to use this representation. For negative x's, it's going to be similar, right? So minus 20,000, that's going to be 0. So minus 1 over 1, that's going to be a minus 1. And for large positive numbers, we're going to get a lot of 1s. And that makes sense, right? Because for large positive numbers, it's going to be 1. And here it's going to be minus 1. Okay. So now let's go ahead and implement the tanh activation function. But before doing that, we need the gradient, or the derivative of tanh. So we know the tanh is e to the power of x minus e to the power of minus x over e to the power of x plus e to the power of minus x. Okay. And we need the gradient of this, that prime. We're going to use this fraction derivative formula. So a over b prime is going to be a prime b minus a b prime over b squared. Right? This is the rule for the fraction derivative. And we're going to apply it here. So it's going to be this prime times this minus that multiplied by this prime, right, over this expression right here, squared, okay? This representation, or this expression here, it kind of looks complicated, but I can assure you it's not. It's actually very simple to simplify this. It's very easy to simplify this. So the first thing we notice here, so this is, we want the derivative of this expression. So what's the derivative of e to the power of x? Well, that's just e to the power of x. What's the derivative of e to the power of minus x? That's e to the power of minus x times derivative of minus x. So it's going to be e to the power of minus x times minus 1. And minus time 1 time, well, so minus, that's going to turn into plus. So minus 1 times minus 1, that's 1. And we remove this here, okay? That's it. For this one right here, the derivative of e to the power of x, that's going to be e to the power of x, and this is going to turn to minus because of the minus x derivative, and the derivative of e to the power of minus x is going to be e to the power of minus x, so remove that. And, okay, we're done computing the, computing derivatives. Now we need to simplify this. Now notice these two terms here, they're the same, right? This right here is the same as this. So this is pretty much the same as that squared, okay? So that's done. And same could be said about these two, right? They're the same. So we can go ahead and replace this with squared. Now, notice that this is the same as this right here. So this can be even further simplified. So we can say this is 1 here minus that, well, minus, let me see, minus this squared over that squared. We can even further simplify this, right? So because it's square over square, we can say we divide this over that. We divide that over that. Actually, we leave this parentheses. And this whole thing is going to be squared. Okay, let me see. Yes, this whole thing is going to be squared. Now, notice that this expression right here, it's the same as this. So it's the same as tanh. So in fact, we actually simplified this to a degree that we actually got tanh x squared, because this expression, again, is the same as tanh of x. And in the actual implementation, we're going to say that that's the same as tanh of x times tanh of x. Done. So that's the, we computed the gradient or the derivative of tanh. So now we're going to go ahead and implement tanh because we know how to implement both a forward method and a backward method. Okay, so for the forward method, as already mentioned, for the negative x's, we're going to use this first, or the like the middle representation here, the middle formula here in the middle, the second formula. And for the positive x's, we're going to use this rightmost or the last formula we have here. Okay, so the way we can do this is we can do a negative mask, and that's it's going to be where data is less than 0, and positive mask is going to be a negation of a negative masks. So it's like pretty much this is going to be a tensor of zeros and ones, and if we flip zeros and ones, that's going to be the positive mask. Turn every 0 into 1, every 1 into 0. Okay, now we can like create intermediate like a variable. I call it z, so you could call it whatever. Empty like data, so it's going to have the same shape as the data, but it's going to be an empty tensor initially. And what I want to have here is that I want to generate 2 times data a negative mask. So what I'm trying to generate here is e to the power of 2x, right? And e to the power of minus 2x. I want to generate those basically values. So that exponentiated, and for the positive, we're going to have minus 2 positive mask. Again, because for the positive x's, we're going to use e to the power of minus 2x. For negatives, it's e to the power of 2x. Okay. Next, we can say, let's define like a numerator maybe. And that's initially going to be torch.ones. Ones, well, it's going to be ones like, we can do it like this, same shape as data. Numerator at the negative mask, we're going to actually multiply that by minus 1. The reason for that is because in the for the negative values, we have minus 1 here. And then we can add z's at negative mask. Right, so we're adding e to the power of 2x. So minus 1 plus e to the power of 2x. This is pretty much the same. E to the power of 2x minus 1, okay? And for the positive mask, we're going to subtract the one with a z at positive mask, because that's minus e to the power of minus 2x. We don't need to multiply by minus 1 because it's positive 1 there. We also need the denominator. And initially, we can do again, ones, a tensor of ones with the same shape as data. Denominator at a negative mask, so that's going to be, we're going to just add e to the power of 2x, right? So we're just going to add z's at negative mask. And for the positive mask, we're just going to add the positive mask, because that's e to the power of minus 2x. So it's both, we're adding e to the power of 2x in one case, and we're adding e to the power of minus 2x in the second case. So we don't really need to do minus 1, multiplication by minus 1 or subtraction. We're adding in both cases. Now, finally, result is going to be numerator over the denominator. And then we just return the result. Okay, that's the forward method, except for we also need to store the result. So the result is pretty much the tanh of x. Because we computed it here, we can then reuse it in the backward method, right? We know that the backward method can be computed as 1 minus tanh x times tanh x, so 1 minus tanh x squared. And it's kind of wasteful, so it's going to be like less performant, right? If we implemented it again here, right? So we better save it. We compute it anyway, so it's going to be some. It's for like a performance kind of improvement here. Save for backward result. And result, of course, that's the tanh that we computed. Now for the backward method, what we're going to do is that we're going to unpack or obtain or extract this result from the context, saved tensors. Then we can compute the gradient, and we know that what's the gradient. It's this, and we can copy this over, okay? What's the tanh of x? Well, that's just the result. Same about the tanh there. So it's tanh of x squared. 1 minus result times result. Finally, we return grad output times grad. So that's the chain rule. We'll multiply the gradient up until this point by the gradient of the tanh activation function, okay? And that's going to be the entire implementation of the tanh activation function. And now we're going to go ahead and test this. For testing, we have this simple test. Of course, in production, we would have a lot more tests, right? But for like a simple test, we can do a grad check. So we're going to use this torch autograd.gradcheck utility function provided by PyTorch. And what that does is that, of course, it compares our gradient approximations to the numerical approximations. And if they're close enough, we're going to say grad check successful. And otherwise, the grad check was unsuccessful. But let's run this. And there it is, grad check successful. So super cool. This means that our implementation is kind of good, okay? Again, in the production, it would have a lot more tests, but this is going to suffice for this simple test. Well, actually, I would suggest you use the built-in tanh that PyTorch has, like you can obtain using torch.tanh, for instance. So in production, that would be the proper approach. But of course, here we're implementing everything, so we need to know how everything works. Now, I want to show you the alternative implementation. So I renamed this to ___ tanh, right? And the alternative implementation, it uses one of the perks that PyTorch provides, namely the autograd engine. So in fact, we don't really need to implement the backward method manually, because all we use in the forward method are the functions and operations for which PyTorch knows how to compute gradients. So the autograd engine is going to pretty much derive or compute the derive backward method or compute the gradients for us. So this is the alternative implementation where we only implement the forward method. We don't have any context. We don't save tensors. We don't compute the gradient. We don't do anything. We don't save the result. We don't even pass context, right? So we just pass self. So it kind of simplifies the implementation. All we need to do is import torch.nn as nn, inherit from nn module, perform inheritance, and define a forward. So it's pretty much the same as here, except for we don't have like the context save for backward. Now the API is going to change. The way we're going to use tanh is going to change. We're going to use this kind of like a class initialization. And that's how it works with the nn.module, right? When we inherit from nn.module, we do initialization like that. In case of torch.autograd.function, we use the this apply, tanh.apply, but with nn module, that's how it works. Okay, so let's run this. And grad check successful. So these implementations, they're kind of equivalent, right? Of course, in this case, PyTorch does work for us, right? It does a lot of work for us. We don't need to compute gradients and so forth, but they're similar, right? Now, this implementation, of course, is a lot more flexible. This implementation allows us to pretty much compute the gradients on our own. This means that in case... So this is the implementation we would use, or this is the implementation route we would take if we were to implement some activation function for which we use operations that PyTorch does not support out of the box, right? For which PyTorch does not know how to compute derivatives, right? So that's why I wanted to show you this approach. But I also, of course, wanted to show you the how we compute the gradient or the derivative and how we use it, right? So also the fact that we use this kind of trick of it's not really a trick, it's just we're simplifying expression to a degree that we can reuse the computations here. So we store result and then we use it for gradient computations. Okay, so this is going to be it for this video. I hope you enjoyed it. I hope you found it helpful and informative. If you have any questions or suggestions, please feel free to comment in the comment section, and I'm going to see you next time.